Hello and welcome to the presentation of the paper towards automated metamorphic test identification for ocean system models. My name is Dilip Hiremat. I am a PhD student at Kiel University and Guiomar under the MAR Data program. I am supervised by Professor Dr. Martin Claus, Professor Dr. Wilhelm Hasselbrink and Dr. Willy Rath. Let's begin with understanding the shortcomings of traditional testing methods for validating research and simulation applications. By its nature, research software are exploratory, non-deterministic, or the end results is too expensive to compute. This unavailability of verified end results to validate the software test runs is termed as test oracle problem in software engineering. Metamorphic testing is a prominent approach to validate software which pose test oracle problem. Metamorphic testing is an approach where a software is verified by comparing the end results of multiple runs of the application with varying morphed input data. Metamorphic relations are the necessary property of a software under test based on which the input data is morphed. If the output is in accordance with the applied morphing to the input data, the test is asserted and the software is verified for that particular test. Identifying these metamorphic relations are cumbersome and cost intensive. Typically, domain experts, after studying the software, identify such metamorphic relations. The proposed method in this paper is to automatically generate metamorphic relations using machine learning for verifying software belonging to ocean system model applications, which is often built on complex legacy codes. We believe this will ease identification of metamorphic relations, increase automation, improve testability and test coverage, and reduce the cost of testing. Metamorphic relations identified can be used to test applications under development, compare different implementation of the constituent functions or software, and since the underlying physical symmetries are constant, the identified metamorphic relations can be transferred to validate other applications representing the same physical systems. In our application domain, we may define a function under test f as a mapping from x to y, where both x and y are finite dimensional normed vector spaces. Then a metamorphic relation g and h satisfies the form f of g of x is equal to h of f of x, where g is the input mapping from the source input to the follow-up, which is the morphed input, and h is the output mapping from the source output to the follow-up output. Here is the flowchart of a metamorphic test. Let the pair function g and h represent the metamorphic relation. We take the original input data denoted by x. We apply the morphing to the original data based on the metamorphic relation to generate the morphed input data, which is denoted by g of x. We feed both of these into the application under test and get their corresponding outputs. We then apply a function h to the original output to get the modified original output denoted by h of f of x. We then compare these two outputs and see if g of x is equal to h of f of x. If the condition is satisfied, then the test is a pass, and if the condition fails, then the test is a fail and indicates an error in the application. Initially, we assume h to be an identity map in f of g of x and h of x. The task now is to find approximations of g satisfying the equation f of g of x is equal to f of x. We also constrain g to be an affine transformation. This retains ability of capturing physical properties related to the symmetries such as invariance under translation or rotation and reduces the solution space. G of x is equal to gamma x plus beta, where gamma is the matrix associated with an endomorphism of x and beta is an offset. Let us assume there are multiple sets of values that satisfy this metamorphic test equation. Let us represent each of these relations as small case g0, g1, gn-1 into a solution set capital G n-1 of function f. We formulate a cost function that rewards a gn which minimizes the Euclidean distance between the atomic data points of the source output and the follow-up output and penalizes for a known g. The implementation of the cost function is as displayed here. The upper term on the right hand side of the equation rewards the cost function and the bottom part penalizes it. We start with G0 being an identity map. Epsilon is a small machine precision constant to avoid division by zero error. The denominator is a product of the square differences to heavily penalize movement towards an already known G. The algorithm we applied is loosely based on the modified genetic algorithm with Monte Carlo optimization. We start with capital G0 of the function f, which is an identity map on X. We assign random values for gamma and beta and iteratively apply mutations delta gamma and delta beta. We calculate the cost for the applied mutation. We specify an acceptance threshold which determines what mutation that increases the cost function is still not rejected. On converging to a minima, we add the newly identified small case gn to the solution set capital Gn. We create a new small case gn plus 1 and randomly assign gamma and beta values and restart the entire process to identify the new metamorphic relation denoted by small case gn plus 1, minimizing for this cost function. To evaluate our method, we construct a sample ocean model application and build errors into this application. We then manually identify metamorphic relations for this sample application and check if metamorphic testing can identify errors built into the application by constructing test cases based on these identified MRs. We then apply the previously mentioned method to automatically identify metamorphic relations for this application and construct test cases based on these automatically identified metamorphic relations and check if the constructed test cases can discover the error built into the sample application. As an example application, we consider the calculation of time series of a kinetic energy of the surface ocean governed by this equation, where t is time, y and x are spatial coordinates, u and v are horizontal surface velocities calculated from sea's level height, eta based on this equation, where g is the gravitational acceleration and f is the Coriolis parameter at 30° north. The coordinate system is cyclically bound in both x and y direction to represent the continuity of the ocean system. To implement the equations numerically, we apply finite element methods. We discretize integral in the kinetic energy equation. We discretize partial derivatives in the horizontal surface velocity calculation. And we link this to the metamorphic relation we previously defined. This results in an input data x, which contains all the discretized values for sea level height, eta, all the coordinates t, y, x, and the physical constants g and f. Now, a metamorphic transformation g of x could change all or part of the atomic data points in the input data x such that the energy of g of x is equal to energy of x for all discrete values of time t. We implement two iterations of the function to calculate the kinetic energy. Implementation 2 does not provision for cyclic boundary conditions in x and y. The artifacts with codes are available through this DOI in the paper. We calculate the kinetic energy outputs for the two implementations of the function and superimpose them. The graph shows that both the outputs vary. To identify which implementation is correct, we apply a few manually identified metamorphic relations to uncover the error. From the graph, we observe that although most of the initial metamorphic relations have similar outputs, the cyclicity in x and y direction vary in output for implementation 2 of the function. This shows that the implementation 2 of the function has an error in handling cyclicity in the sample application. With the proposed method, we are able to identify MRs automatically. We encounter the following challenges. The identified MRs are a chain of multiple elementary constituent MRs, which are challenging to explain in terms of physical symmetries because the conditions might not represent a realistic physical ocean. Also, with this method, MR corresponding to functional states of the software are not identified. Further work would be to apply dimensionality reduction techniques to decompose identified chain MRs, explore other algorithms and optimization methods, remove the constraint of G being an affine transformation, and to relax H being an identity map. These are a few of the references that we used while preparing these slides. Thank you for your attention. Please let me know if you have any questions.
Well, hello again. We are in the Q&A slot of the paper toward automated metamorphic test identification for ocean system models. And we have here with us one of his authors, Dilip Hiremat, who is more than happy to take your questions. Please remember that you have to write those in the chat so we can ask them verbally. Well, in the meantime, there is no question. Hopefully, people will fire away during our discussion. In the meantime, Dilip, let me ask you. There is a first one from Alastair. He says the idea of using a non-identity function as h is interesting. Do you have any ideas of what alternatives could be?
From the papers that I've read, mostly it's one of the interesting things that I saw that they say they add a constant or multiply it with a constant and say the result has to be additive or a multiplicative of it. That's the easiest one. And the other one is you subtract a few data points, or so in my case, in the sea surface height energy, so I subtract a few data points, so that will definitely reduce the end result. Those are easier ones. But what I'm trying to do is also look at the data points that are being changed while identifying the identity metamorphic relations and trying to alter them, and then see if the non-identity function for H can be used. So yes, they can be used, but that's the one that I'm going to explore later on. That's one of the things that I want to do as well. Move from affine transformations and also remove the identity matrix. But it might require, if I want to include that into the cost function, it will require remodeling the cost function again.
Okay, thank you. Thank you very much. Well, I have a question myself. If I understood well, Dilip, you don't only apply metamorphic testing to ocean system models, but you also propose a method for the automated identification of metamorphic relations, right?
Yes.
So my question is, could this method be generalized for identifying metamorphic relations in other domains? What do you think?
Yes. True. Yes, that's one of the research questions that I propose. While applying, that's what one of the things that we propose. The idea is first is to prove that MT can work in ocean system models, and then to identify them automatically. So the next step after automatic identification is to see if the identified MRs can be applied to similar ocean models, not specifically to the SUT under test, but something similar which is also based on the physical ocean, because the governing rules are the same. I'm hoping we will be able to port this, not port, but transform the same identified metamorphic relations to test those. And if by doing that, we'll understand what and to what extent can those be transformed, and what is the required transformation. With that, one of the things we hope to do by the end of the PhD is to look at curating some set of general MRs specific to certain domains and see what are the transformations that we can apply to these MRs, so it can be applied to similar domains. So we can categorize the domains into some major ones and use those specific domains. So that is one of the key points that we intend to achieve later on.
Okay, I see. There is another question from Alastair. He says, am I right that in your domain where things are continuous and potentially elusive, whether something is or is not a metamorphic relation might not be completely clear cut? For example, could there be something that could be a true metamorphic relation over real numbers, but might not work as a metamorphic relation with computer arithmetic due to rounding?
Yes, rounding is an issue. We do consider that while defining the MRs. Uh, Yes, but what we're also when you look at it, rounding becomes a big issue, and when you can convert the physical things into computer algorithm, there's always some abstraction which we need to take care of. But what we're also trying to focus on is to not only identify general MRs, but also try to decompose it, which are very similar to physical ocean constraints that can be used as MR. So as a physicist, they know that certain MRs should always apply. Like if I increase the sea surface height, or if I rotate the globe axis of the data points, the end result should not vary. So there are certain constraints that hold in the physical ocean. What we're trying to do is we're trying to see if automatically we can not only identify the MRs but also decompose them so that they're very similar to the physical constraints. Thereby, we avoid or reduce issues with converting them to algorithms, computer arithmetics. Sorry.
Okay, thank you, Dilip. Another question, Dilip. Very often the problem is not only identifying metamorphic relations. I mean, sometimes it's relatively easy to come up with many metamorphic relations. For example, in web services, it's really simple. And then the problem becomes, and then there is another problem, which is prioritizing metamorphic relations, selecting those which are more interesting, more helpful, we are expected then to be more effective. My question is, was this your case? I mean, do you feel the need, do you have the need for prioritizing metamorphic relations?
I mean, yes, we foresee that there will definitely be the case where we'll have to categorize them into test suits and see which test has the maximum efficiency. We either in terms of code coverage or in terms of defect identification or in terms of identifying which of the MRs are very distinct from each other and not a repetitive or additive or a combinatrix of those. And yes, prioritizing is something that we will look at, but we are not at that stage yet. We are still looking at identifying multiple MRs as of now. And then eventually, if we have, definitely when we have a lot of MRs, prioritizing them comes into play to define a test suite and also on which aspects.
Okay, you are trying to generate diverse metamorphic relations in a sense,
Yes.
right? All right, my final question is, how do you plan to use this in practice? I mean, do you plan to generate and run metamorphic relations 24/7, for example? Would you like to do that? Or I don't know, for example, combining this with a fuzzer that generate input continuously? How do you plan to put this into practice?
The fuzzer idea is good. Based on the paper that is going to be presented next on, we haven't looked at fuzzer. We did consider that, but not specifically in collaboration with metamorphic testing. As of now, we're just looking at standalone systems and not a continuous run. So I have a software and a test or a small function of the ocean modeling system, which is going to be added. So that thing needs to be tested. So we are not looking at continuous thing. We're looking at an offline version where I run them, identify metamorphic tests, define a test suite, run them, get the results, and then look at pushing them. But continuous integration is a good idea, but as of now, we have not looked into it.
Okay. Well, we have only 2 minutes left, so let's thank Dilip again for his wonderful presentation and his the answer to the question. Thank you very much, Dilip, for your talk and for participating in the workshops. For the rest of you, let's see. I'll see you in 2 minutes. Remember that now we have the last presentation that will be presenting the Best Paper Award. Okay, I mean the paper receiving the Best Paper Award. So stay there for the presentation. See you in a minute.
Thank you for your attention. I'm glad to be here. See ya.